The next talk for the Y 2025 in Cassiopeia is Retrospective Adventures in CircuitPython. It will be presented by Juergen, and have fun with it.
Okay, well, thank you for being here. Let's start off with something about me. I do security management work for a living, and I tinker around at night. I've done from assembly language to XSLT, which was the last item on a alphabetical list of programming language that I found. That was the last one that I knew, so I guess it's that. I'm from Germany, and I've spent some time in the US, if you can tell from the accent. So, agenda. An introduction. So that part doesn't really contain any CircuitPython parts, well, a little bit theory. Projects, that's all about things I've built with CircuitPython. And retrospective is then about what works really well with CircuitPython, what doesn't, And then we got a Q&A in the end. So let's get started. First off, some context. My smart home setup. I used to have it run on OpenHAB and just had everything connected to it via the bindings that were offered from it. I also used to have a lot of Z-Wave devices. And I've switched at some point a couple of years ago to Home Assistant. Some things I still have directly integrated. Most of the stuff and almost everything that I talk about today, I have connected through MQTT, so coupled. Oh yeah, and I switched to Zigbee, but that's not of really any relevance for right now. So next up is a picture of in our kitchen, side of the fridge. So just to get an idea of what we're going to zoom in now, we're going to zoom on the display. This is sort of the control center for the smart home. It's OpenHAB and it's Home Assistant UI, and essentially got a few things configured there that I can manage. I think this is what's loading, it's the road traffic. But yeah, that's just to give you an idea, that's where I control stuff from. What you probably didn't notice is in that frame, and this is a 7-inch frame that's made by a company in Italy called Me System, I think. It has a compute module. And I modified the frame so I could put a microphone in there. So I have voice control as well. And that's what we're going to talk about next is I have another project which is probably bigger than everything that in some that we talk about today. It's a HAL 9000. It's a personal voice assistant, so like an Alexa without cloud. Everything is running on a Pi 02 wireless. And the important part to take here is that I use a Python project called Calliope, which does the interaction logic. So this setup is the same inside the HAL as with the smart home controller. The hardware is different, obviously. So the next part is I also set up a matrix channel. Matrix, the messenger. Work in security, so it has to be end-to-end encrypted, authenticated, blah blah blah. I'm using the matrix Eno bot, and the bot used to be purely command oriented. So you'd send a command ping and then something, and it, if you configure it, it would ping a system or whatever. I implemented some room logic, so depending on what room something was received on, it would do a certain command. So I have one room. If I send it like a time and a TV channel, it'll add that to the recording list. So I've set it up so on my TV app I can just share the recording information for a given show, and it'll just do that. What's shown in the picture here is actually some commands issued to the vacuum robot. So the first one is Robby soll saugen. Robby, which is the name for our vacuum cleaner, start cleaning. And it responds with, okay, start cleaning. Then the next one is a voice command, so essentially just a voice message, does the same thing, so speech to text, same logic as with the smart home controller and the HAL 9000. So now we get to CircuitPython. So who has experience with CircuitPython? Show of hands, please. 3, 5. Okay, who has experience with MicroPython? The same, but more. Okay. There were some that didn't raise their hand. So MicroPython is a small Python interpreter. It's developed specifically for embedded controllers, so it's really memory conscious, etc. So aimed for small devices. So it implements a subset of the Python 3.9 runtime, and the CircuitPython is a fork of MicroPython by Adafruit. And what they did is they tailored it for ease of use, and they set up a build system so that especially their boards, but a lot of other boards from other manufacturers are readily supported with CircuitPython. And the major drawback in terms of Python 3.9 versus 3.10 or later is you don't have the match and case support, so you have to write if cases for handling stuff. But they're using support, so that's good. And you know, it's company driven Adafruit, but they're really active, and a lot of things are going on there. The CircuitPython fork keeps on drifting away from MicroPython, but Adafruit, every now and then they just merge some stuff that they deem reasonable to be merged into CircuitPython. So they're not drifting completely away from each other, but it's an off-spin. So just something that's different. Just as with MicroPython, CircuitPython supports all the common hardware that you find in current microcontrollers. So you have the Wi-Fi, Bluetooth LE, which is Bluetooth by name, but really it isn't really Bluetooth. It's just a sibling, and low energy. So the UART is essentially a serial port. You have I2C, which is a serial bus. Then you have 4-wire, which is another serial bus. SPI is a parallel bus. SPI is a serial bus, if I remember right. You can do PWM, which is pulse width modulation, so you can generate analog signals. And one interesting thing is that on some devices, microcontrollers most often nowadays have some sort of USB connector, usually USB client, so you connect it to your laptop so you can flash, etc. But some devices also have USB host capability, so it can be the host to some other USB device. Of course, that has to be supported in hardware for software to have any chance. So next up, firmware library. What comes with CircuitPython, or for the most part also with MicroPython, sys, this probably from regular Python. So board and microcontroller are obviously very hardware specific. OS is a rather empty module. There's not much aside getenv in there. Supervisor is a module with which you can control the Python interpreter running on the board. So restart an application, set an application to run on next boot, or whatever that you can do. And then you have a subset of useful packages like JSON message pack, which is just a binary thing, so a serializer. Hashlib, zlib. With zlib, it's interesting to note that due to the limited amount of CPU power, they can only do decoding. They don't really do encoding, so zipping stuff. I tested it, I can't remember which project, and zipping something really takes forever, even for just a 4K file. So what is really awesome about CircuitPython is that they already provide a community bundle. So what you get when you install CircuitPython is a ready-to-run image that you can just flash on your board. That brings these modules and some more. But they have a library that you can just download and is ready to use that has at least 100, maybe 200 or so libraries in it, and you probably find everything in there. One special thing to note, and they sort of exist in MicroPython as well, but in CircuitPython they are different, is workflows. What are workflows? That's stuff that runs in the background, so things that are not running inside the Python interpreter. So USB, if you want to expose like a USB drive, that's a workflow in CircuitPython. If you want to have a Wi-Fi connection, that's a workflow. If you want to use Bluetooth Low Energy, that's a workflow. So stuff running in the background of the interpreter. Next part, and I just mentioned this, CircuitPython by default exposes part of its flash as a USB drive. So let's say you have 256K or 512K of a flash. I don't know, half of that we used for code, for the CircuitPython runtime, some a little bit for data that's used internally, and the rest is then used as a FAT file system most commonly. So when you plug in the device using USB, then it'll show up as a USB drive that you can write to, and that's actually where you write your code to. So the CircuitPy drive, that's what it is. For this to work, obviously there has to be hardware support so that the flash chip can interact with the USB controller. So there are some boards that have a serial USB controller on it, and that just exposes a serial line. So with that you don't get the CircuitPy drive, but CircuitPython has using like with the Wi-Fi and the Bluetooth, other ways to connect to it. But obviously with the hardware that is able to expose and act like a flash drive, the most comfortable part. So CircuitPython, when it starts up, it looks for boot.py. That's the only place where you can really do hardware setup. So if you say, I want to use Wi-Fi, you have to do it in there. If you want to, do some very specific power management setup, you have to do that there. Once that's done, and this file just runs once, every time after reset, code.py gets loaded, and that's where your application lives. And this is sort of like in the Arduino logic, run over and over. So if it exits, it'll just run it again. And then there's setting.toml, which is a sort of like an ini file, but a little bit a YAML file, and you can configure values in their key values. And those you can access using os.getenv. When you do that, you have to understand that os.getenv loads the toml file every single time. So if you want to get 30 different keys from it, it'll in the background load it 30 times and unload it, etc. So not the best performance. There's a toml library that you can use to just manually load that and then access it, in RAM, but that's in terms of costly as with RAM. And if you just, like from the community bundle or whatever, you want to use libraries, you can put them in the lib and just import them, and they're there. So that concludes the introduction. Let's get to the fun part. First off, room audio. What's room audio? We have an audio system in every room. It's we have Sonos, but it could be pretty much about anything. And I wanted to make use of that with more than just being controlling it from the app, or from the controller in the kitchen. So I created like a software system I call Brickies. Why that's the case, we'll see on the next slide. And it consists of 4 services. So you have readers. Those are things that trigger something. Then you have services. They are the ones that provide content. So a local MP3 server, Spotify, Amazon Music, whatever. And you have players. Well, they're the audio devices, right? And then you have an agent that coordinates everything between that, and also has a GUI. I have a short video clip of that. This is in the my son's room. So I put in an RFID card. It has a label on it. The label or the ID of the RFID card is entered in the database. So the the reader reports the UID of the card that was inserted. The agent will look up what is the matching content, what is the matching player for that reader, because you don't want to put the card in my son's room and for it to play in my daughter's room, right? So handles all that. And what was probably not audible, but while the card was playing, it was playing the intro of Peppa Pig. So the code for that is... No, I think we'll get to that later. But so essentially what you see here, the reader is an implementation of Bricky's reader through CircuitPython, right? So next up, personal audio. You probably know the Tony box, right? Portable music player for kids. Put a little figure on top, has an RFID chip, it'll play whatever is assigned to it. Well, this is pretty much it. So I designed it with a Lego theme, and that's where the Brickies name comes from. On the right-hand side, that's the inside. So the left hand just shows the top shell that just slides over. Not entirely, because the RFID reader is missing on the right-hand side on the top. So that's another 5 millimeter of a piece that sits on top of it. And the idea here is that I drill holes into the Lego figures and just use push, like the bullet style RFID tags to insert them, so it has a UID to read and act upon. So this device is both a reader and a player, because obviously it does play the music. Next up is something really hot off the press. This is a device I just stumbled upon just a couple of months ago. No, not even months, a couple of weeks ago. It's called a Mighty 3. It was a big Kickstarter thing like 5-10 years ago, whatever. As my kids don't have a MP3 player, so to say, yet, I got them each one of those. And the way you use it is you have an app. The app talks with the device using Bluetooth LE and provides the access credentials for a wireless network. So what the device will do, it'll connect to Wi-Fi, it'll download whatever is on Spotify or on Amazon Music, and then you can just navigate through it. And the headphone jack is also the charging connector. So you have a little USB to the 3.5 millimeter thing. You plug it in, it charges, and then it's ready to receive commands on over Bluetooth LE. So my idea is to build a charging station where I just, where my kids insert the player. It'll detect, okay, player is inserted, so it'll look, is there new content, like a new podcast episode, whatever, and then sends it as a command to the the mighty 3. I created the repo, but there's nothing in it yet. Why? Because the next slide will show you like where I am. So I asked the manufacturer, hey, can you give me details about the protocol that you speak using Bluetooth LE? Oh no, sorry, corporate secrets and intellectual property. Sorry. So I stared at bits, and after a couple of minutes, I was like, that might be message pack, and it was. So it's using just regular GET, which is just a hey, write this string in this property on the device. So the property might be the command channel. All right, and what you see here is the interaction from the app with the device, already message pack decoded. So it's almost always a list of 7 segments. The first item is the command or status code. The second appears to be a sub-status command or code. Then the next 2 vary, and then the last one is a payload, I guess. So the first line is the app says, hey, I'm the Android client. Okay. The next command is, oh, I got a new podcast episode for you, little device. And it's from one of the shows my kids like to listen to. And then in white, the device responds, hey, okay, I'm the mighty client. And what follows then, the long segment towards the bottom, is essentially, okay, I'm connecting to the network, and it's the in bold. So at home media is the network assigned to it, and yes, the credentials when you set up the device, the app credentials will pass over Bluetooth LE, unencrypted, message impact the device, but that appears to just happen at configuration time. So probably not too bad of an issue. What goes on then at the bottom is essentially the device says, okay, I got your command to download this episode, and I'm starting it. The Spotify episode and the ID, that's what really Spotify URIs are. So if you know the Spotify API, will recognize this. So the last line towards the end of the before the breaks, says something. Let me go back. It says, go back. Not that far. Okay. Let's see. Can we go forward? One more. There we go. So you have 2 pairs of lines that are identical. Essentially, it's saying my download progress is 0.0. It hasn't started the download yet. But the last line says, where is it, 3.4 or something? So the next lines are just the percentage of until it completes downloading everything it's been told to. So the idea for the charging station is to just send exactly those Bluetooth commands to the device. So you just saw it. The next one is a receipt printer, just like you see in the stores. I hooked up a Pi Pico wireless to it, and this is an Epson TM23 or something like that. It has a USB port, so the Pico running CircuitPython talks to the receipt printer using its serial port, and the Pi Pico is the USB host in this scenario. So as the Pi Pico doesn't have a USB host implementation in it, it can't do that natively, but the PyPico has something that's called PIO, programmable I/O, in which you can have little microstate machines running at essentially clock speed, and that's good enough to emulate low-speed USB. So CircuitPython has an implementation where it can configure some of the GPIO pins as USB host. So that's the wiring. I don't know if it's really that readable. Let me see. I have a laser pointer, so if you can see the screen, well, it's not. Can't see it on the screen. Okay, but there's some wires dangling off the top of the PyPico. That's the cables that end up in the USB port of the device. The thing in the front is actually just a voltage converter, because the receipt printers, they have something that's called a kick drawer. Essentially, something to open the cache drawer, and that has I think it was a 24-volt line. So this is a buck-down converter to USB, has a USB connector, and that's just the power feeding into the PyPico using its native USB port. What do we do with that? Well, mostly I print shopping lists with that. So using smart home lists, etc., I do shopping lists, and then I just print it, and I go into the supermarket, and they end up at the cash register and keep looking at it. Did I forget anything? And they are always sort of like, why does he have a receipt in his hand? What does he want from me? Is there a complaint or something? And I'm like, oh no, that's just my shopping list. I'm done. But my kids like to do these little mazes, so plenty of use cases for that. What is the CircuitPython app about? It's an AskPos server. AskPos is the format that drives the receipt printer. You can just send it a plain ASCII, it'll print it, but just like as in the shell environment where you can do color coding, it's fixed and stuff. So that's how these mazes get generated, and essentially it can take SPOS from MQTT or over HTTP or using TCP. That's a raw connection then. You probably guessed it, I connected using MQTT in my home assistant setup. So, next one is one that my son really liked. It's a Lego train controller. Who here remembers these controllers that you used to have for trains back in the day, where you could, turn the dial and then the train would drive? Yes, I got one of those on eBay, gutted it, and put in a rotary encoder, and I think it was an ESP32, and it works. It's driving, so my son can use one of these to control his Lego train, which the next video is about. So there's the train going. That's a bit old already. He's got a lot more tracks since then. Some were bought, some were 3D printed, but Okay, so next up, some not. Was there a question? No? Okay, so this is a Halloween costume. It's essentially an LED strip mounted like a wrist headband. My son is wearing it on his forehead. He had 2 buttons in his hand. In that was the, I think it was a PyPico, don't remember, with 2 buttons, and he could control it switching in from glowing red or glowing white or just blinking and stuff. So that was the costume he had worn the last 2 Halloweens. And the next one is completely off topic. It's a CircuitPython board in the form of a USB stick, and what it does is it doesn't expose the USB drive. So the workflow for USB is disabled unless you push the button, so there's nothing here to see. If you push the button and have in the background established a Bluetooth LE connection, only then will it present its contents. So when it lights up green, it'll go back on, and you'll see the USB drive. So proof of presence, essentially, of the owner is the idea. That's completely finished, published. Yes, so that was it as far as things that I've done. Let's take a look at how does CircuitPython handle all that stuff. So I said in the beginning, like they aimed CircuitPython to be easy to use, and that really starts with the installer. You get a device, you bought it somewhere, and with quite a few devices, all you have to do is go to the website, select the device, and then it has a button, Open Web Installer. And what I'll do is using Web USB, which is implemented in Chrome-based browsers, it'll open a serial port connection through the USB connection to the device and flash CircuitPython on it. So it's really plug and play for some boards. Other boards you have to flash manually, you have to download it. Some boards you can do UF2 installer, so you download a file, you get an empty file system, drag and drop the UF2 file on it, and it'll flash it, and also very easy. And some boards you have to just spin up command line and flash the image. What's also good is you can, and that's for I've used that quite a bit for getting my hardware for the next project. Like, okay, I want a board that has speaker, a joystick, a USB-C port, and you can see if it returns anything. So that was sort of my shopping list filter, just to so I could get the most suitable board for the job. Yeah, I talked about that already, the UF2 and web installer. So there's more good things. So with Python in general, you've probably acquainted with a fast development cycle, and the same is true here. You load your code onto the USB drive, and by default, in the moment you update a file, the supervisor, the module that controls the Python interpreter, will reload. So in the moment you save, it'll reload the application, and you immediately see what's running. So the result of what you did, which might be an error code, if you just saved at the wrong moment. But hey, async is also fully supported, but you don't get the usual Python async libs. They have some CircuitPython special libs, which are memory optimized, etc. In the video with the USB stick, it said debug mode. What was debug mode? Debug mode is all the files on the USB drive were in Python files, so .py, so source code. So what the interpreter has to do when loading the application or importing a package is interpret the source file, build the instruction, the abstract syntax tree, etc., and then run it. Well, that step can be done beforehand. That's the MPy cross-compiler, and M in that case is for MicroPython. So CircuitPython just carried on with that. So you just compile it, put that on the thing, and that really makes a difference. So you saw the whole cycle took about, I would say, 25-30 seconds with the USB stick. When you do that with MPy files, the whole cycle takes like 7 seconds. So day and night. And the best way to really optimize all that is to have a minimal boot.py and a minimal code.py. So the amount of parsing that's required by the interpreter is minimized, and just load the code from a cross-compiled MPY files. And when you're developing, sometimes you want to do it still on your laptop. So there's Blinka, which is a CircuitPython runtime that uses a POSIX runtime. That's really cool in terms of developing on your laptop when you might not be able to bring along the device or whatever. But there are differences. I think we'll get to. No, I'll mention it on the next slide. We are now to the downs. So the idea of the USB storage in terms of the initial design from CircuitPython was, let's present that to the host as our CircuitPython data drive, right? So that's always there. So the user is always able to modify that, etc. And so the amount of APIs that are present to control the state of this is really just one thing. You can unmount the file system of the Python interpreter, so it doesn't have any file system at all anymore, and that results in the USB drive being ejected virtually. You can remount it, but you have to beforehand get the handle to the VFS, the virtual file system, before you unmount it. So you have to jump through a little bit of hoops to do reloading of the USB drive, because the way the USB storage thing is implemented is that from the PC side, when it says, okay, there's a USB drive, it sees just a block device. So it sees something that has sectors of bytes. The file system is actually interpreted by the operating system. What the device sees, it just sees, okay, I want to write these bits in sector 32. So CircuitPython has a hook in that whenever a sector changes in the USB drive, which is essentially just bytes in flash, it'll do a reload on the file system. So, okay, I see you just changed that file. And then it says, okay, let me reload the interpreter or do whatever. The other way around, when you write some file to the backing flash storage, the operating system doesn't get that, because it's assuming a drive is passive. It doesn't expect for it to be changed in the background. And that's why you need the eject and remount, so it knows, okay, something has changed, or it's fresh again. Bluetooth LE. What's really easy is saying, okay, just scan for devices. Oh, I like that device, make a connection to it. Perfectly easy API. When you want to connect to a certain device that you are not scanning for, but you know its MAC address, etc., can do that. The API CircuitPython provides there is really limited. If you want to do stuff like that, you really need to go to MicroPython. What's also an issue is you have boot loops. So your code executes but fails out and just restarts. You end up essentially in a boot loop. Maybe even it does a reset. And if you don't have a bootloader, where on most common devices they have a reset button, if you double press the reset button, it'll boot to bootloader mode. If you don't have that, if you have buttonless device, you're stuck. So what you need to do is you need to implement some kind of recovery logic, like 10 resets in the last 5 seconds. Okay, let me just not do anything. Let me drop out into a shell mode, so someone connect using a serial shell, or just access the USB drive and fix whatever has gone wrong. And the last part is nitty gritty, but so Bluetooth LE, USB, Wi-Fi, these are the main workflows CircuitPython provides. Well, the first one you configure using an attribute that you set to true or false. The second one you call enable or disable in a completely different package. And the last one for Wi-Fi, you just have to set an API, like a setting in the settings toml file. So not exactly straightforward. On the upside, that's well documented. So it's more of a well, why isn't this coherent? So I've got 10 minutes left. We're in the last part, Q&A. Before you can ask questions, I would like to ask you questions. I've shown you some projects that I haven't released yet to the internet. Do you have any preferences what I should work on next? So the Brickies thing is the whole ecosystem of the music player devices, from the Lego portable device to the reader and stuff, everything. The Lego train controller, the Mighty 3 charging station, or the Halloween headset. Any preferences? If so, raise your hand. So who's for brickies? 2, 3, okay. Lego train controller? Also 3. Mighty 3? 1, 2. And Halloween? 2. Okay, so I guess it's brickies and Lego first. Let me do the Lego first because that's the easier one. That'll be finished first. So, okay, with that, I'm done. On to your questions.
Thank you. Are there any questions?
Just want to know how well does the voice control work?
Okay, so this is not CircuitPython related, right? It's a side project that was just relevant to why do I need the reader, etc. The voice control, the Calliope. So when I was building the HAL 9000, it started when the Pi 3B came out, and I was like, that ought to be good enough to do speech to text on chip, right? No cloud. That turned out to be right. But the error rate was awful. We're talking about 20% word error rate. Every 5th word was wrong. And the reason that is the dictionary they have, the list of words that they know, the speech representation to what it is in text, is huge, like something like 50,000 words. So that might be that word, might be that word, I'll take that one, So 20% word error rate. The solution to that is obviously to reduce the dictionary, right? So if it has to pick 1 out of 200, it's much less error-prone than 1 out of 50,000. So I looked around for essentially these, let's call them agents, right? Personal assistant frameworks, where you'd be able to specify the exact commands you wanted to issue. And that's how I ended up with the Calliope, where you actually have to define every variant of what you want to have as a spoken command. It supports variables, play Paw Patrol in kitchen, right? So it knows then something is the title, something is the location, play, okay, yeah, we can figure that out. And from Calliope, I stumbled upon Vosk. Vosk is a open source project by some Russian company that has gained some traction with Home Assistant in the last year with their speech first strategy, whatever. And the combination of those two matched the exact requirement. With Calliope, I defined the commands, and I use those commands to reduce the dictionary in Vosk. And the error rate in real life is 0. nothing. I mean, I get errors like I couldn't even tell you when the last speech-to-text error that I had when I interacted with it. I can't even tell you when that was. It might have been this year, it might have been last year, That's really awesome. The key to that is having a known vocabulary, so you know what the dictionary should be like. The one issue that I still have, that's something that's on my to-do list, multi-language, because Paw Patrol isn't in the German dictionary. So what I do for the variables is I simultaneously send it into the German and the English model, and just see which one returns something useful, and if both return something useful, in terms if it's the music piece, the audio piece, then I look up which one do I find in the database. But that's proof of concept stage right now. So yeah, completely side project, but yeah, that's how I got there. Okay.
Are there more questions?
Okay.
No more questions. So, thank you.
No. Well, I have thank you as well. So, We came here, we brought a bit too much beer. So there's free beer at our village. That's what it looks like. We're right next to the Jetto workshop on Seinfeld. I gave away lots of hardware, and this is hardware that's been left over from lots of these projects that I did, because this is just the projects where that sort of I finished, or am going to finish. I have twice or three times as many projects that were like, oh, that sounds like a cool idea. Oh no, let me put that aside, and put it aside. A week later, it goes there, and a week later, it goes into the box, and the box go to every camp. So those are the boxes that are given away. The things that are still left are USB cables, adapters, power adapters. So if you're in need of any of that, just come take it. I would hate to take any of that stuff back and put it in my basement. It'll just come up to the next camp. But come and drink our beer, please.
Thank you, Juergen.